this lecture we'll be discussing about cyclic voltammetry. It starts from voltammetry. It's electrochemical method in which information about an analyte is obtained by measuring current as a function of applied potential. That means it measures current as a function of different potential applied. And cyclic voltammetry means if the process is cyclic, that means once it gets reduced, then again after applying potential it will oxidize, and that means applied potential will be like that starting from a potential, then after reaching some potential again it comes back to that initial potential. If it comes to that initial potential, then cyclic voltammetry, then it's called cyclic voltammetry. The CV is also electrochemical, where current measures the current as a function of potential. Here the component requires for CV. And CV requires working electrode, counter electrode, reference electrode. These are the three types of electrodes required in cyclic voltammetry. Working electrode, this working electrode, reference electrode, and counter electrode. Working electrode actually used for oxidation reduction of analyte. That's on the surface of that electrode, oxidation of or reduction of analyte occurs. And reference electrode, for reference, that means with respect to this electrode, potential measures. And counter electrode that for current flow. And in solvent, this solvent part is important because to measure CV you cannot use all solvents. There have some solvent selectivity for different analytes. That means according to your analyte you have to choose that solvent, because every solvent has solvent window. Solvent window means a certain range of potential within which that analyte, that means solvent, gives good result. And then nitrogen gas supplier to make inert atmosphere, supporting electrolyte to minimize or eliminate migration current. Okay, those for supporting electrode. Supporting electrode actually some compounds with bulky groups and also ionic parts as well as ionic ends as well as bulky groups due to steric hindrance and that means volume, that supporting electrode eliminates or decrease that migration current. And in CV, measurement of current, whatever current is measuring is actually diffusion current. Diffusion current means current due to concentration gradient. This voltammetry depends upon this equation, the Analyte equation, where IP measures IP, not a potential, and that IP peak current, relationship peak current and scan rate, this nu, this root nu, this rate current, scan rate, and concentration. If we increase concentration, then peak will increase, peak current will increase, because more number of analytes will get reduced or oxidized. And then scan rate, if we increase scan rate, then again P will increase, IP will increase, because increasing scan rate means changing potential in less time, taking less time to change potential. And in CV we have told that change in, that means it measures current as a function of potential. Okay. And this is one CV of an analyte. Here this is negative potential, that means this side potential is decreasing and this side higher potential. And this current for reduction of analyte, because if we decrease the potential, then analyte has a tendency to reduce itself after reaching some certain potential. In this potential, reduction of analyte starts, and then here the maxima, where maximum number of analyte reduces, and then again it's decreasing. And then once it gets reduced, complete reduction of the analyte, again the increase in potential, that will occur oxidation of that analyte, whatever of that reduced species, oxidation. This current is for oxidation of reduced species, reduced analyte. Okay. And this side, then complete reduction, oxidation of reduced species. This is for reduction, and this is for oxidation. This maxima here, after reaching some potential, some analytes are reducing, and then reducing. Okay. And here is maxima, where maximum number of compound gets reduced. Okay. Then and here Nernst equation is useful for analyzing EPC and EPA. EPC is potential at its maxima for reduction. Right? Now, using Nernst equation, we can make a conclusion that why that EPC, that peak cathodic current, potential of that peak current EPC, that potential is lower, that this side is decreasing, lower than standard potential. But that potential where maxima, okay, so in case of oxidation of analyte, this maxima is actually at higher potential. This potential is increasing at higher potential than standard potential. It can be proved from Nernst equation. In Nernst equation, there is, if you consider reduction of a species A plus E minus is equal to A minus, then equation will be like that: E is equal to E0 minus RT by NF ln A minus by A. Okay. N is number of electron, that means 1. Okay. And then suppose consider here N, and then ln A minus by A, this part if we take, okay, it will be N by F by RT, E0 minus A. That is, if you take this left hand side, and then E0 minus E, and then RT by NF ln MNSN. This will be left side, and after that that NF will come up, and then RT will come down, and then come this position. Okay, that from this equation, okay, A minus, that means reduced species. To make reduced species more, okay, to make reduced species more, this right hand side should be positive. Okay, so only the condition is that if E0 is greater than E, only then reduced species, concentration of reduced species will more if that standard potential is greater than EPC. This is EPC. That's means potential at which maximum current, peak current occurs for reduction. Okay. So from here we can conclude that in case of reduction, that potential at which maximum reduction occurs should be less than standard potential. And similarly, for similar case for oxidation, to make A minus more, E must be greater than E0. From the previous curve, what can we determine? We can determine redox activity of analyte. That means analyte is reducing first, that means at some certain potential reducing once, then again it is getting reduced. If an analyte has a tendency to reduce twice or thrice or four, according to that means nature of analyte, at different potential also analyte can reduce or oxidize differently. So redox oxidativity, that redox activity of analyte, that means the analyte is reducing once or twice, that we can measure. From the equation, that IP current is equal to this current, that we can comment on linearity of the plot of IP versus this. This is scan rate. IP versus this. More linear means more reversible, that oxidation and reduction, that will come later on. Then this del EP is equal to EPA minus EPC, vary with scan rate and concentration. How do the values of del EP is equal to del EPA minus EPA vary with scan rate? That means if we increase scan rate and concentration, how this difference varies, that also can determine, and then can comment on EPA and EPC using different scan rate. That means EPA or EPC is getting changed or not. But for reversible, will come later. For reversible, EPA and EPC not change, or reversible oxidation not change with respect to scan rate. Okay. Then can be calculated del G, K, equilibrium, and then entropy. So how do we know the process is reversible or not? Here is it. If this is EPC and here potential is decreasing, here reduction after here oxidation of that reduced species, that EPC, potential of peak current, that potential of anionic current. Okay. how do we know the process is reversible or not? Here, if IPA is equal to IPC, then we can say that process is reversible. That means oxidation reduction is reversible. That means this IPC, the height of IPC and height of IPA is same, then process is ideal reversible process. Okay, couple is process, oxidation reduction is. Peak position are related to formal potential of redox potential. And then EP0, that means standard electropotential, is equal to EPA plus EPC by 2. If it happens, then we can call that process is reversible. Then separation of peaks for a reversible couple is 0.059 by n volt. That means this separation of current, this separation, okay, where IPA at around some potential and IPC at around some potential, this potential difference between IPA and IPC for reversible process is 0.59 by n. N is number of electron that is getting reduced, number of electron that is by number per electron that needs to reduce any voltage. And peak potentials are independent of scan rate. That means this, if we increase scan rate, that means changing potential in less time, okay, then what will happen in case of reversible reaction, whatever scan rate, it doesn't matter, but that the potential EPC, the position of EPC will be same, only will increase IPC or IPA, but EPA or EPC will remain same for reversible couple. Okay, the position will remain same, just will increase that current, potential will remain same. And the effect of scan rate on reversible process, here current, this side current, this is voltage, this, look, this potential EPC and EPC and EPA remaining same, just only increasing that current if we increase scan rate, because if we increase scan rate, we are taking less time to reach this potential, and current is directly proportional to 1 by T. That means if we decrease the time, current will increase. That's why increasing scan rate, current increases. And this consideration, the difference between reversible process and irreversible process. Here, for reversible process, potential is remaining same in with respect to scan rate. Increasing scan rate, current is increasing, but position is remaining same of that potential. But for irreversible process, that potential, position of that potential is deviating. Okay, this is due to that electron transfer process are slow relative to the voltage scan rate. That means in case of reversible process, here at this certain potential, maximum number of analytes are get reducing, but once we increase that scan rate, in case of irreversible process, maximum number of analyte is reducing at more low voltage, okay, due to slow process. That means it cannot reduce that much amount of analyte at this potential. And then these are that if we apply potential, negative potential, that means that negative potential means the electron will stay higher energy level in case of that electrode. That electron will be higher energy state because it's negative potential, negative, and hence that electron jumps from HOMO of that electrode to but when we decrease the potential, in case of decreasing potential, in case of oxidation, once we increase the potential, energy level in case of electrode becomes lower, and hence that HOMO from electron from HOMO of that analyte jumps into that energy level of electrode, LUMO of that electrode, because its energy is lower than HOMO of that analyte after certain potential. Then thank you. Hope it really helped you, and have a nice day.